Hello and good morning, everyone. Uh, can someone confirm that you can hear my voice clearly?
Yes, sir.
Yes, sir.
Okay, let's go. Okay, today we are going to study the unsymmetrical bending for the unsymmetrical sections. In the previous class or the previous 2-3 classes, we have studied the unsymmetrical bending for the case of symmetrical section. For example, we have this I section, which is a symmetrical section, and we calculated the bending stress for this section. If I recall, what we have done in that method is that we would calculate the moment of the loads were acting actually in the inclined direction, and we would calculate the resultant movement due to these applied loads, and we would transform those movement onto the principal axis, right? Usually in the case of symmetrical sections, we have the principal axis coinciding with the symmetrical axis, which are usually the horizontal and vertical axis. So we will have some kind of an inclined movement in this case, and we will transform this movement onto the principal axis, and then based on these two moments which are on the principal axis, we would apply our flexural formula, which is my over I, because this formula is only valid for the moments that are acting on the principal axis. So now in the case of unsymmetrical section, for example, let's say this is an L section on which the load is acting in the straight axis or in the vertical direction, and we have this centroidal axis for this one. But in this case, this centroidal axis is not the principal axis, because the principal axis is one on which the product moment of inertia is either is zero, product moment of area is zero, and moment of inertia is either maximum or minimum. And Ix, or let's say Iy, is either maximum or minimum. So in the case of L section, since it is not a symmetrical section, we may have the principal axis somewhere over here. But the methodology that we have to follow for this L section is same as that we done in the case of symmetrical section. What was that? That if this is the applied load, again we will calculate the moment. But in this case, let's say this load is acting in the vertical direction, so the moment will be produced on an axis or around an axis which is 90 degree to this axis, and this which I have shown by this black line. And let's say if I resolve the moment by following the same sign convention as we have done in the previous case of the symmetrical section, let's say this is my movement M. Since I cannot apply this flexure formula on this moment M, again I have to resolve this moment on the horizontal axis onto the two principal axes, and in this case this principal axis are these one which I have named as y and z. So now I have to transform the moment onto these inclined axes or the inclined principal axis to apply this flexure formula. So the concept is same, only difference is the change of directions or the orientation of the principal axis. Another question is that how will we determine that what is this or what is the moment of inertia on this inclined principal axis? Actually, there are transformation equation just like we have done for the case of stresses and strain. That if we know the stress on one axis, which are basically horizontal or vertical axis, we have developed some equation using which we can calculate the stresses or strains on any inclined axis. The concept is similar for the case of these section or this moment of inertia, that if we know the moment of inertia on one axis, we can transform it onto the inclined axis. But that part is not included in the scope of the this course, so we are going to skip that. But again, I will give you some reading notes. If someone is interested, they can do the derivation of this transformation equation to calculate the moment of inertia on any inclined axis. But in this course, how we are going to get it? Actually, for every section, these are basically the standard section, and there are section tables available for each section that we are going to solve. And in these section tables, we are given this orientation of the principal axis for any type of unsymmetrical section or the symmetrical section. So we don't need to apply this transformation equation. Actually, they have already applied this transformation equation on every type of section, be it the L section or the Z section, or let's say even the circular section. So for any type of section, we have these section tables, and in this section table, we are given this moment of inertia on the principal axis and also the orientation of this principal axis with respect to the horizontal axis. So using that section table, we can calculate directly the value of the principal axis and the orientation. And another method is using the radius of gyration. In some of the section tables, the direct values of the moment of inertia are not given, but we have been provided with the values of radius of gyration. Basically, radius of gyration, you already know, is the property to relate the moment of inertia and the area. So this radius of gyration is different for different axes. So in this section table, this radius of gyration is given for the horizontal and vertical centroidal axis and also for the principal axis. For example, if I have been given the radius of gyration for this y-axis and I know the area of this cross section, this area is also given for every section. And if I know the area of this cross section, or area is for the whole section, it's not dependent on the axis. So if I know the area of this section, I can apply this formula to calculate the moment of inertia on this principal axis or on this y-axis. So now if we know this moment of inertia, this inclination, then again we will apply same concept of flexural formula and moment transformation and calculate the bending stresses for this unsymmetrical section. And another important point that we do need to consider in this case, for example, let's say, or I can draw it here. Let's suppose we have this Z section, which is an unsymmetrical section, and this is my centroidal axis for this Z section. I will name it as Y. Y dash, and this as Z dash. These are my centroidal axis, and let's suppose that these are my principal axis, which I will name as Y and Z. And this is the inclination of this principal axis with respect to the centroidal axis. Now, if I want to calculate the bending stress, let's suppose at this point B, which is the top one, at this point B, and I have to apply this flexural formula, which is basically my over I minus, let's suppose, mz over I. Now this y distance, what is this y distance? Actually, this distance is the perpendicular distance from the axis, right? For example, in the case of straight section, we will take, if this is my z-axis and I want to take this y distance is from, for this B point, this y distance is from the centroid to the top of the section on the straight axis, if my principal axis are the horizontal or the vertical. But in this inclined case, my principal axes are obviously not horizontal or vertical, but they are in the inclined direction. So my y distance or this z distance will also be inclined distance. So let's say if I want to calculate the bending stress on this B point, this will be the y distance that I have to substitute in that formula. Let's say I will call it as yb. And similarly, what will be the z distance? I have to replot this diagram. This is point B. So the y distance will be this perpendicular distance from the centroid to the B point. Let's say I will call it as YB. And similarly, what will be the Z distance? Z distance is also the perpendicular distance from this axis, from this Y axis towards point B. Let's suppose this distance will be ZB. Now for each cross section, you can calculate, if you know this orientation and if you know the horizontal Y and Z distances, then you can calculate these two distances by using simple geometry or the resolution of these two horizontal and vertical distance. But again, that can take a lot of time. So we can develop one simple equation, and which will be the universal equation, and we don't have to do the geometrical procedures every time. And we will have one equation and we will simply apply it and convert the straight distances into the inclined distances based on this angle theta and the straight horizontal and vertical distance. Let's see how we can do that. Let me plot this diagram again. These are the centroidal axes. These are the principal axes. This is my point B on which I want to calculate these distances. This is angle theta. This I will name as phi dash, and this axis is the z dash. This axis is y, and this axis is z. This distance is ZB, and this distance is YB. This angle is theta. Now this distance is YB. Can I say that this distance, this red line here, is also YB?
YB वाला डिस्टेंस कहाँ से कहाँ तक है? वो तो चले 20 से, और ये Y वाला कहाँ से आ गया?
YB?
हाँ जी.
YB is the distance from the centroid to the point B, perpendicular distance.
अच्छा.
Because if you look into this, like for example, if I want to calculate the stress at point B and I have this black axis, let's suppose these are my principal axis. What will I do? I will take this distance or the straight distance from centroid to this B point as my Y distance, right? So same is the case for the inclined axis, or if my principal axes are inclined, I have to take the perpendicular distance which will approach point B. So this is my YB distance. Did you get my point? So can I say that this distance YB is equivalent to this distance YB over here? Which I have shown by this red line. This distance is equivalent to this distance which I have shown over here. So what will be this distance? Can I say that it is ZB dash? Again, if I show the symbol by dash line, it means that the distances are on the Z dash axis or the Y dash axis. If I show the distance by simple YB or ZB, that will mean that these distances are with reference to the inclined axis. So you should make these things clear in your mind. So this straight
सर ये
distance,
90 डिग्री है इसके कॉर्नर्स
which corner?
मतलब ये जो दो जहाँ पे इंटरसेक्ट करें ये 90 डिग्री है ना
This one.
जी
Yes, it is 90 degree.
और दूसरा वाला भी इसके बिल्कुल जो ऑपोजिट है
This one?
जी नहीं सर ये जो मतलब सही है सर
Is it clear? Okay. So this straight distance is ZB dash, and this straight distance, actually this line I have shown in a bit inclined, but it is basically a straight line. So this straight distance is YB dash. But from this horizontal axis, perpendicular distance towards B point is YB dash. And this angle again is angle theta, which is equivalent to this angle. Okay, and this angle is also angle theta. So what will be YB? Can I say that YB?
सर ये एंगल वाली बात
Yes.
कैसे कर रहे हैं आपने क्या बताया ये थीटा जो दो बनाया
Actually, first thing is that this line or this green line is basically a straight line. Okay, so as I have shown that what is YB dash? YB dash is distance from the horizontal axis towards point B. So this is YB dash distance, and this red line is basically this line equivalent to this one. So this distance over here is YB, let's say, and this angle with respect to the inclined axis is angle theta. So basically it is the same angle theta which is over here. I have just shown it on the left side, let's suppose. So this distance or this straight distance is YB and this inclined angle is angle theta. Did you get my point?
Yes, sir.
Okay. So what is YB? YB is basically the sine this component plus this component. Okay, so what is this component over here? Can I say that this is ZB dash sine theta plus this component will be YB dash cos of theta. Is there any confusion about this one?
सर ये मुझे ये नहीं समझ आया दोनों थीटा सेम कैसे हैं ये जो रेड में आपने लिखा हुआ है और ये जो ब्लैक में लिखा है
Actually, the angle theta is basically the orientation of principal axis with respect to the with respect to the horizontal and vertical axis. So let's suppose that my horizontal and vertical axis are these black ones, and I rotate these axes by an angle theta to reach the principal axis. So this rotation is angle theta. If I rotate one axis by angle theta, obviously this horizontal axis will also rotate by angle theta. So both of these angles will be the same, right? Right?
Yes, sir.
So this is why both of these angles are same. So what will be ZB now? Can anyone tell me what is ZB? Or can anyone resolve this? You have 1 minute. Just try to think about it from this figure. If you want to write ZB in terms of ZB dash and YB dash, what will be ZB?
Sir, can you please identify YB dash or ZB dash कौन सी line है? Mechanical fluids.
YB dash. This red line, this one, which I have shown over here, is YB dash. Sorry, this red line is YB. This green line is YB dash, and this red line is YB. Over here, I have shown it. So this red line is YB, and this green line is YB dash, and this horizontal line is ZB dash.
So ZB dash cos theta minus YB dash sin theta.
Yes. So actually,
सर ये YB dash सिर्फ sin theta नहीं होगा?
which one?
सर ZB.
ZB. What are you saying?
YB dash sin theta.
No, you have to look into this figure to figure out what will be ZB. Just try to think. Why it will be ZB? What are you saying? Why B dash sine theta?
Yes, sir.
Why will it be like this? Because YB dash sine theta will be this distance which I have shown by the red line, right? So ZB is the distance over here. This one. So it can't be the same distances, or it cannot be the only YB dash sine theta. So anyone else? So let's look into this figure. If can I say that this distance over here is ZB dash cos theta?
सर वो
Yes.
सर जेड बी डैश कॉस थीटा और माइनस वाई बी डैश साइन थीटा सर ये गलत है
No, it's not wrong.
अच्छा
Okay. So this whole distance is ZB dash cos theta. What will be this distance? If I look, if I say that, let me show it with another pointer. Let's say that this whole distance, this distance is ZB, and this whole line, which I have shown here by the green pointer, is equivalent to this bottom line. Okay. So in this line, actually this is making things confusing for you. Let me do it again. So ZB. So these are my centroidal axis. This is my point B, and this is the inclined axis. This distance is ZB. Okay, and this distance over here is ZB dash. Let's suppose we have this line over here. This distance is Y. This should be over here. So this distance is YB dash. This is angle theta. So I need to find out this distance, which I have shown in the red markers. Okay. So if we look into this figure, so what is this distance? This whole distance from this point to this point is ZB dash cos of theta, right? So what will be this distance? This one. Can I say that this distance is YB dash sine of theta? And I am interested in calculating this distance. For example, this whole line is equivalent to this one, and I know this whole distance is ZB dash cos theta, and this distance is equivalent to this one, which is YB dash sine of theta. And I need to compute this distance, that is ZB. So what will be ZB? ZB will be ZB dash cos of theta minus YB dash sine of theta. So can I write it over here? ZB dash cos of theta plus minus YB dash sine of theta. Now, is there any confusion about this one? If you have, you can ask me right now. So there is no confusion, then we can move on to the example problem. So now I have these two formulations for YB and ZB. If I know this ZB dash distance, which is basically the distance on the straight axis, for example, if I want to find the stresses at point B, and I know this ZB distance and YB distance for this point B, and I know the inclination of this angle, this principal axis with respect to the horizontal axis, then I will simply apply these formulation to calculate these perpendicular distances. And About the sign convention of this formulation, we have developed this formulation based on the positive z dash axis and y dash axis. So for example, let's say if I have a point over here, let's say this is my point D, and I want to calculate the yd distance and zd distance. But for this point D, my zb dash distance will be on negative z axis. So I will take zb dash as negative, and similarly for y dash distance, it is also on the negative y dash axis. So both of these distances will be in the negative direction. So this is how you have to consider the sign convention. And similarly for angle theta, in this figure you can see that we have considered the orientation in counterclockwise direction. So if the orientation of the principal axis with respect to neutral axis or the horizontal or vertical axis is clockwise, then I have to take this angle theta as negative. So again, for these kind of question or for these type of derivation, it is very important for you to keep this figure in your mind. So everything, if all the distances and all the angles have the same orientation with compared to this symmetrical axis or compared to these figures or these axes, then you can take all these directions and angles as positive. But if any direction is opposite to this one, because now this is our reference, so if any direction is opposite to this one, you have to put in the negative sign. Another method, obviously these are the formulation, and there is we have developed based on some resolution of forces or resolution of distances and moments, but you can always resolve this by simple algebra. But again, this will take a lot of time and will make things confusing. So I will suggest you to remember or memorize this formulation and these figures. Is there any question? 542. Who are you? So let us solve one simple example, then you can better understand this concept. So we have this L section on which a load of 1 kilopound is acting at the center. The distances are 24" on either side, and we need to compute or calculate the orientation of the neutral axis and the horizontal axis. And the second thing is we need to calculate the maximum bending stress in the beam. And this is our cross section, which is L6 by 4 by 1 by 2. So let me first show this cross section. So when you are solving these kind of unsymmetrical section, the first thing that you should know is how to read the section table. Let's suppose that this is my L section, which is given in the question, and L6 by 4 by 1 by 2. So what are these dimensions? What does these dimension mean? L6 means the length of the longer side. So in this one, if my longer side is this one, so this whole length is 6 inches from this dimension, and this distance will be 4 inches. And this 1 by 2 means the thickness of this two legs. So this is 0.5 inch, which is given in the question. L6 by 4 by 1 by 2. So the next step is to figure out the distances of the centroidal axis. This we have to do from the section table. So let's move on to that one. Now this is the section table, and in this table you can see that over here this is L6 by 4 sections. Okay, and next to this one we have been given the thicknesses as well. So our section that is given in the question is L6 by 4 by 1 by 2, which I have shown by in this red triangle. This is the section under consideration, which is given in the question. So from this section you have to look into this figure as well and these distances. So now if I want to look that what is these are my centroidal axis y and x, and if I want to know that what are the distances of this centroidal axis with respect to the extreme left or extreme right of the cross section, then what are these distances? You can look into this figure that this y distance is given as 1.98. Basically, what is this y distance? Y distance is the distance from the horizontal axis to the extreme bottom of the section, or to the extreme bottom of the shorter dimension of this cross section. So in our figure, let's say that this y distance is given as 1.98, and our section is the same as this one. So in our section, what will be this y distance? This y distance is from this point, which is the horizontal axis, to the extreme top of the shorter leg, and this distance is given as 1.980. So what will be this distance? Anyone, just give me this distance quickly. Yes. So we know these two distances. So then next step is what? Can you please turn off your mic? So next step is, what will be this distance? You can also get this distance from this section table. So let's look at this table again. And this distance is the x distance shown over here. And from this table, you can see that this is 0.981. So again, I will substitute this distance 0.981 over here. And this remaining distance will be 3.02 inches. So now you have these distances. And the other thing is, what will be the orientation of the principal axis? I have told you that it will be also given in the question. So now look at this section table again. And this inclined axis, which is z axis over here, is basically the principal axis. So for these inclined axes, you can see from this table that this angle alpha is given, which is basically the orientation of this inclined axis with respect to the centroidal axis. So now we know, and we know the orientation of this principal axis. And another thing that we have been provided in this question is this radius of gyration. So for this z-axis, the radius of gyration is 0.864. And we have also been provided the area as well of this section, that is 4.75. Now, as I have told you before, that since we know the area, we know the radius of gyration, we know the angle alpha, so we can calculate everything, that is moment of inertia, angle, and these two things, and this is what we will need in this question. So the area that is given in this table is 4.75 inch square, which is the area for the whole section. The radius of gyration that is given in the question for the, let's say these straight axes are the y-axis and z-axis, y dash and z dash axis, and these inclined are y and z axis. So we have been given the radius of gyration about this y-axis, so which is 0.864. Now don't get confused with the name of the name of these axes. For example, in the section table, they have been named as x and y. So it's better that we should follow the names as we have did in our derivation to make things convenient for us. But you can obviously use any names, so it doesn't matter. So the radius of gyration about this y-axis is given as 0.864, and tan alpha or tan theta, which is basically this angle or the orientation of the principal axis, is given as 0.440. So we should name it as tan theta, that is 0.440. Okay, now all these things I have got from the section table. Now the first step in this type of problem is to compute the moment of inertia about these principal axis, because we do need them while we are calculating the bending stresses. So first thing first, what is this angle theta? That is tan inverse 0.440. Give me the answer quickly.
Sir,
Yes.
ये जो थीटा जो अल्फा वो सेक्शन टेबल में गिवन था और ये जो
Yes.
थीटा ये दोनों इक्वल हैं, मतलब
Yeah, it is basically that alpha.
बट सर वो अल्फा तो वर्टिकल एक्सिस के साथ है ना?
Okay, that alpha is basically the angle between the vertical axis and the inclined axis. Let's say it is that angle, vertical axis and the inclined axis. Okay, so now calculate this angle theta. These two angles will also be same actually. So what is this angle theta? Let me show you.
23.75.
23.75. And what will be this angle now? 90 minus 23, right? So I think it will be something 66 degree. And again, this angle will be 23. So you have got the answer that these two angles are same angles. Okay. So now we have these angles, and the next thing is we need to calculate the moment of inertia about this principal axis. So what will be the moment of inertia about this y-axis? We know the radius of gyration. So Ry, or I can use it as ARY sphere. So I know Ry, I know the area of the cross section. So Iy will be 4.75 into 0.864 whole square. So what is Iy?
Let's say 3.54.
Inch 4. Now I know the
ये भी
moment of inertia.
सेक्शन टेबल में नहीं गिवन होता आई वाई वगैरह भी?
Actually, in some section table it is given directly, but in some section table like this one, they have given you the radius of gyration and the area, so you can also calculate by this one. Or in some question, it will be given to you directly that these are the moment of inertia about the principal axis and this is the orientation. So you don't have to look into the section table at all. So, but you should know every method to get this one. Now I know Iy. Now what will be Iz? Actually, in the section table as well, you will be given the radius of gyration only about one principal axis. And from the transformation equation, just like we did in the case of stresses, that if we know the stresses on the horizontal and vertical axis, then the sum of stresses on these two axes will be equivalent to sum of the stresses on any of the inclined axis. So same is the case for these moment of inertia. This thing, just consider it as one formulation that if we know the stresses or the moment of inertia about these horizontal and vertical axes that are Iy dash and Iz dash, then the sum of moment of inertia about the inclined axis, or let's say about the principal axis, will be same. So now I know Iy dash, I know Iz dash, and I have calculated this Iy, and I can compute this Iz. So let's look at the table and see what is Iy dash. So from the table you can see that this x-axis is our basically z-axis over there. So the moment of inertia about this horizontal axis is 17.3, and the moment of inertia about this vertical axis is 6.22. So I can write it over here that moment of inertia, my vertical axis is this y dash axis. So moment of inertia about the vertical axis is 6.22 inch 4, and moment of inertia about the horizontal axis is 17.3. So this I have got from the table. So now what will be my Iz? Anyone?
19.974.
19.974 inch 4. So now I have got everything that I need to solve this question. So from this point on, this question will be same as for the symmetrical axis. So let's start solving this one. So the first step is obviously to figure out the direction of movement or the resultant movement. So how will we do that? This is my beam on which one cap of load is acting. So obviously in this one also we need to compute the maximum bending stresses. So for maximum bending stresses, I need to have maximum bending moment over the entire cross section, or I need to figure out where is the maximum bending moment acting and what is the magnitude. Okay, so again I will go into the bending moment diagram to figure that out. So let's suppose that this is given in the question that this load is 1 kip and these distances are 24 inch. So what will be this reaction? 0.5 and 0.5. So my bending moment diagram will be something like this one. So what is this peak, or what is the value of this one? That is 12 kip, right? 0.5 into 24. So now I have this direction of I have the magnitude of bending, maximum bending moment that is acting on the entire cross section. So if you remember in the question that we solved in the class, we will consider the resistive direction of the bending moment to be placed in the cross section when we show this bending moment in the cross section. So in this one, if you see that this bending moment that is 12 kip is acting due to this force that is 0.5, right? So this bending moment is being produced in the clockwise direction. So what will be the resistive bending moment? It will be in counterclockwise, and we know, or we have developed one sign convention that if the resistive bending moment is in the counterclockwise direction, it will be pointed in the outward direction in section. So if I want to show this maximum bending moment on the cross section, so I have this L section and the force of 1 kip is acting over here. So as we remember that this force will produce the bending on the axis which is at 90 degree to this one. So that axis is this Z dash axis, and this force will produce the bending around this axis. Okay, so bending is being produced around this axis, and what we used to do, we would place our beam on this axis, or we will just suppose that our beam is being placed on this axis and we will plot the direction of bending moment. So in this, from this figure you can see that this bending is being produced on the left side, so I have to show the bending axis or the bending arrow on the left side, and since the direction or the orientation is outward, so it will be shown in this direction. So that is my resultant bending moment of 12.
सर
Yes.
ये आपको हमने ये कैसे निकाला कि जो 1 के फोर्स लग रही है ये इसी पॉइंट पे लग रही है?
Actually it is given in the question. This one. This orientation is, yeah. So now this is my direction of bending moment. Now if I again plot, so we can erase that. So this is the bending moment, and we have to show it by double arrows to differentiate between the loads and moment. Now if I again plot my principal axis, these are my principal axis, and I know the inclination of this bending moment with respect to principal axis, that is 23.8 degrees. Okay. So the first thing that they have asked us to compute is to calculate the angle between the neutral axis and the horizontal axis. For that, this figure or this derivation is very important to understand. So let's suppose now I'm solving the first part of the question, that is to compute the inclination of neutral axis. So let me plot this section again. So this is my L section, and these are the centroidal axis. So I will assume that the neutral axis is passing through the center. Wait. Is passing through the centroid, and this is the bending moment. And this is my principal axis as well. So these axes which I have shown by the blue lines are my principal axis. This red line is the neutral axis. This is the neutral axis. These are the principal axis. So I know the orientation of this moment, that is 23.4 degrees. So if you look into this figure, which things you need to calculate, or this is my formulation, that is tan beta is equal to Iy over Iz into tan alpha. So let us look at this figure. Sorry, this is basically, if this is z axis, Iz over Iy. Z is the horizontal axis and Y is the vertical axis. In this figure, this is the Z axis and this is Y axis. So what is the angle beta? Angle beta is basically the clockwise angle from the horizontal axis. Now you have to look at it carefully, that this horizontal axis is basically the principal axis. So in this unsymmetrical section, our horizontal axis is basically the inclined axis. So in our case, the angle beta will be this axis, this angle from this inclined horizontal axis towards the neutral axis. So this whole angle will be angle beta. And from this figure, you can see that this angle theta, which I have shown as angle alpha over here, I can name it as theta. So this angle theta is basically the angle of the angle from the principal axis or from the horizontal principal axis towards the resultant movement. Okay, so in this figure you see that this is my resultant movement, and this z axis is my principal axis, and this is the angle theta from this principal axis to the resultant movement. So now I know that what is angle beta, what is its orientation with respect to the principal axis, and what is angle theta and what is its orientation. So this angle theta is in the clockwise direction as well from the, if we take this axis as reference. So this will be positive, because in this example we have derived this sign convention based on this one, that if this orientation over here, you can see that this orientation with respect to the horizontal axis is clockwise, we have to take it as positive. And similarly, the orientation of neutral axis, if it is clockwise with respect to the horizontal axis, then we have to take it as positive. Okay, so this tan beta will be, what is Iz? We have calculated it. I think it is 19.9, and Iy.
सर
Yes.
हमने जो शुरू में डेरिवेशन की थी,
Yes.
जिसमें हमने y भी, तो उसमें हमने थीटा काउंटर क्लॉकवाइज नहीं लिया था.
Theta. Actually, both of these derivation and both of these sign convention, again, I am reminding you that you have to remember the figure based on which we get or we derive any particular formulation. So for example, for neutral axis, we had this figure, and we have to take this as our reference to be used in this formulation. You can't use the same sign convention in every formulation. And for the derivation of YB, where is it? Here, yeah. So for the derivation of YB, obviously our sign convention is this one, and in this sign convention, our angle or angle theta is counterclockwise positive. So that's why I told you that you need to memorize. If you want to use any formulation, you need to memorize the figure or the diagram on which we have shown the sign convention. So those sign convention will be positive and the other one will be negative. Yes.
सर लेकिन वहाँ पे अगर हमने काउंटर क्लॉकवाइज पॉजिटिव किया तो जब हमने वैल्यू इसकी निकाली थी तो यानी वो पॉजिटिव थी तो वो काउंटर क्लॉकवाइज थी, तो इस केस में भी वो काउंटर क्लॉकवाइज नहीं होनी चाहिए, तो फिर हम नेगेटिव यूज़ करें।
No. Actually, we didn't calculate any value from that one. We simply made one derivation. Okay. So in this formulation, for example, if I when I will be applying this YB and ZB, I will consider that sign convention that counterclockwise is positive and clockwise is negative. But I will use this sign convention only in these two formulas. Okay. But in this one, I can't use the same sign convention because I have derived this formulation based on this method. Actually, this sign convention is nothing basically. You can always solve these questions by algebraic um, resolution of forces and moments or whatever is the case. And these sign convention are based on what or based on the conditions that we considered for the derivation of formulas. So for every formula, there is one figure on which we have shown our positive. And if that is the case, then we will use the positive symbol. If not, then we have to use the negative symbol. So you cannot apply that condition that counterclockwise is positive in this one. You have to consider its own figure and its own sign convention. Did you get my point?
सर मुझे ये समझ नहीं आ रही कि अभी पीछे करें जहाँ पे हमने एंगल निकाला था 23
Yes.
वाला, तो अब यहाँ पे ये पॉजिटिव था ना, तो इसका
This angle.
जी ये पॉजिटिव था, तो अब यहाँ पे
Actually,
ये क्या है?
no.
काउंटर
This angle is neither positive nor negative. Okay. We need to know the reference. This is my horizontal axis, and I will read this angle as the counter from with. If I want to read this angle with respect to my principal axis, so this angle with respect to my principal axis is in the clockwise direction. Okay, with respect to my principal axis. So now look into this figure. In this figure also, this angle theta with respect to principal axis is clockwise, right?
Yes, sir.
So this is what I am doing. From this figure, I have calculated this angle theta that is 23 degree, and I will read it. If I want to read it with respect to the principal axis, which is z axis, this angle is in the clockwise direction. So same is the case over here. I simply know this value. It depends on my figure that with respect to which axis I will read this angle. With respect to the principal axis, because I have done my derivation with respect to the principal axis, this angle is clockwise, so I will take it as positive.
Okay, sir. Thank you.
Is it clear?
Yes,
If you have still any confusion, you can ask me because I know these things are confusing. Yes, someone else is asking question. Is there any question or I can move on?
सर इनिशियली हम लोग जब हमने स्टार्ट में पढ़ा था तो आपने बताया था कि जो मोमेंट होगा वो हमेशा जो न्यूट्रल एक्सिस के अबाउट होगा। जब लोड जब परपेंडिकुलर होता है तो हम लोग ये कंसिडर करते हैं कि मोमेंट जो है उसके परपेंडिकुलर वाले एक्सिस पे प्रोड्यूस होगा, मतलब उसके अबाउट होगा। तो इस केस में जब लोड जो है वो परपेंडिकुलर था और हमने मोमेंट भी परपेंडिकुलर एक्सिस पे ही कंसिडर किया, तो वही न्यूट्रल एक्सिस नहीं होगा, मतलब ये वाला न्यूट्रल एक्सिस और वो उसमें कंफ्यूजन है।